Welcome back to GFE0007, Data Analytics Made Easy for Beginners, and we are on Chapter 4, which is on fitting a model to data. So, introduction to modeling. So the focus of today is fitting model to data, and this is where we really start to see the magic of how machine learn from information. And we will start with the introduction to modeling. And before we look at the formula, we need to understand what we are actually trying to achieve. So now we want to ask the question, what is a model? So simply put, a model, as being mentioned in the previous lecture as well, a model is a simplified representation of reality which is created to serve a specific purpose. So we take from the previous example as well. Think of the map analogy. So if you are looking at a road map, it highlights the road and the topology, but it ignores the individual trees or building because they are not important for navigation. So similarly, a data model may highlight the key variable while ignoring the others, which we call as the noise or the random fluctuations in the data that don't really help us to see the bigger picture. So now we differentiate between the predictive and the descriptive model. So the predictive model is like a formula to estimate the unknown value of interest, which we call it as the target or the target variable. So for example, a telecommunication company might want to ask, will this specific customer will leave our service next month? So on the other hand, the descriptive model is about gaining insight into the underlying phenomenon. So instead of predicting one person's behavior, whether or not they will leave or they will stay, we may want to ask, what do our typical churning customers look like? And this will help us to understand the general trend. Now let's do a quick terminology refresher. So we have already covered this in the previous example, but just freshen up a bit. So the instance, or we can also this at example, is just a single data point, like one row in your Excel spreadsheet. It may represents individual. So the attributes or the features, or sometimes we also call it as variables, are the columns that describe the instance, such as age or income. And the target variable is what we want to predict. So when we create a model from the data, we call that a model induction. And the data we use to teach the algorithm is what we call as the training data. So in the previous lecture, we covered the induction tree. Now we want to go beyond decision trees. So what other models are there? Now let's recap a bit on the supervised segmentation. So previously we used the decision tree, which we partition the data into regions using the axis parallel boundaries. And think of this as a series of rectangular boxes where every data point belongs to exactly one path leading to a leaf node. So like last time, we start with one feature which is being employed or not, and then we look at the balance in the account. So now we look at the new approach. Okay. The decision tree are a piecewise classifier where they cut spaces into finer and finer rectangles. But what if your data follows a diagonal trend? And to fit the diagonal line using a tree, you'll need a staircase of many vertical and horizontal splits, which is a bit inefficient. So the solution is to use a mathematical function, which is an equation, to define a single and could be potentially diagonal boundary. And so it introduces us with what we call as the linear discriminant function. Okay. So now we look at the mathematical model structure. So instead of searching for splits, like we split employed to be employed or not employed, and after that balance is less than 45 or above 45. So in this model, we specify the structure of the model first, and then we leave certain numerical parameters unspecified. Because our goal in data mining is to calculate the best value for this parameter based on our training data. And this is what we call as the parametric modeling. So the linear model equation, this is the generalized linear model, which is expressed as the weighted sum of these attributes. So we have the function of x, which is given by w0 plus w1 x1 plus w2 x2. So here, the x variable are the attributes values or the features. So let's say x1 is the employment status, x2 is the balance, and so on. And w is the weight, or what we call as the parameter. And w0 or w sub 0 here is what we call as the intercept. So this intercept acts as the offset. So now let us understand how this linear classification works. So the function fx here, it may output a certain score. For example, if someone's employment status is whether 1 or 0, so we put 1 if this person is employed, 0 if not employed, and x2 is the account balance. So let's say the account balance is 38,000, so we just put 38,000 here. So based on the value of w0, w1 and w2, so we can actually compute what would be the functions of x here. Okay. So this is how the linear classification works. So the function outputs a score, and then we then use a decision rule to discriminate between the classes. So the rule is, if the class of x is positive, if f of x is greater than 0, and then it belongs to the negative class if f of x is less than or equal to 0. So after we compute the fx here, let's say the value is above 0. If it is positive, then we put them into one class. If it is 0 or a negative value, then we put them into different class. And that is how we discriminate the results or the score. Now, we can visualize this geometrically. So in the two-dimensional space, the boundary looks like a line. But in 3 dimension, it looks like a plane. And in a higher dimensional space, we call it as hyperplane. And points that are far from this boundary are scored with high confidence, while those who are close to it are considered as uncertain. Now let's talk about optimization and objective functions. So in the training set, there are often infinitely many lines that can separate two classes perfectly. So which one do we pick? We may need a way to define what would be the best fit looks like. Okay. So first is we use the objective function, where this objective function represents our goal. And we calculate this function for a specific set of weights and data, and then we find the optimal model by either maximizing or minimizing it. So as a data scientist, we must choose an objective that serves as a good proxy for our actual business goals. And then we can look at the loss function, which represents the error penalty for prediction. So 0 and loss is simple, which is we set 0 for correct and 1 for incorrect, but it is not mathematically convenient for optimization. The squared error, on the other hand, is used in a linear regression, and the squared error will penalize grossly wrong predictions very heavily. And then there is a hinge loss, which is used in support vector machines, which penalizes points based on how far they are from the correct side of the boundary. So next we introduce the support vector machines, or SVM. Now let's look at the intuition behind the SVM. So SVM are a type of linear discriminant. So instead of using just a thin line, we imagine fitting the fattest bar possible between the classes, and the width of this bar is called the margin. So why do we maximize the margin? Because if we have a new data point, and we know that this new data point will be scattered, so the fat margin will give us the maximal leeway to classify these new points correctly, and then it will make the model less sensitive to small movement in the noise, small movement or noise in the data. And then we also want to address the misclassified points. So the real world data is very rarely perfectly separable by a straight line. So basically SVM, they use a soft margin to balance between the two goals. The first goal is making the margin as wide as possible, while at the same time we also want to penalize points that would fall on the wrong side. So the next model would be the linear regression, so which is the most commonly used model in machine learning. So we see that the linear model is not just for classification. Earlier I showed you the example of the linear regression used in classification. But in fact, linear regression is mostly used for numerical. They can be used to predict the numerical and continuous value. Like for example, we want to answer the question of how much will this customer spend. So the structure remain the same as the weighted sum. For example, like we have fx is given by the intercept, which is w0 plus w1 plus x1 plus w2 times x2. Okay, and in this case, because linear regression is numerical model, we do not have to reclassify fx into other categories. Okay, now we talk about the least squares regression. So the goal of the least squares regression is to minimize the sum of squares of the error. So the question is why we want to minimize the sum of squares of the error, but why not just minimize the sum of the errors, but we need to square them? Because it is mathematically convenient, and it will also penalize or strongly penalize very large error. So imagine if the difference between the actual and the predicted is 1. So you take 1 squared is also 1. But if let's say the distance is 10, so 10 squared is already 100. So this is how we penalize errors, especially large errors. However, the drawback of this model is that it is very sensitive to outliers. And now we want to talk about the logistic regression. So this logistic regression is suitable for when the target variable is category, and then it has two categories, yes and no, churn, not churn, something like that. So when we talk about logistic regression, we talk about estimating probabilities. So sometimes in business, the yes and no question is often not enough. So we might also want to know the probability that the transaction is fraudulent. So in this case, logistic regression would be the standard workhorse for this task, where we can put the threshold. For example, we can put like the threshold at 50% or 80% or any other numbers, depending on the problems that we have at hand. So in the logistic regression, we use in this logistic regression, we use the logit trick, which is we run on the standard linear model output scores from negative infinity to positive infinity, but probabilities must be between 0 and 1. So to fix this, we use the log odds, which is the log of the quantity P divided by 1 minus P equals W sub 0 plus W sub 1 times okay, I don't have to read this, yeah. And this will create the sigmoid curve, where this is the S-shaped curve, which ensure that at the decision boundary where the score is 0, the probability is 0.5. So this is far from the boundary, and the curve approach 0 or 1, which squeeze the output into a valid probability range. So how do we fit the logistic regression? We use what we call as the maximum likelihood. So the maximum likelihood will find weight that make the observed data most likely to have occurred. How do we do this? We give high probabilities to the positive examples and we give low probability to the negative ones. So next is we look at the comparisons and the complex models. And here we compare between the linear models to the decision trees. So what are the differences? Number one is when it comes to the boundary directions, the tree splits perpendicular to axis, while the linear model can go to any directions. In terms of the local and the global equations, so the trees are more piecewise and localized, while linear model use a single global equations which can be used to all of the observations. And then finally, when it comes to variables, the trees select one attribute at a time. For example, starting from the root node, we choose one variable and then it's split into two or more categories, and then we consider another variable and so on. But the linear model, it has a fixed equations in which the linear model actually used the weighted combination of all of them at the same time. So the next one is we consider comprehensibility. Okay, so in terms of the interpretations, the trees are considered as highly comprehensible because it can be explained by the rules, the if-then rules. For example, if employed, then then what will be the result? If this variable is larger than a certain value, then something something. So comparing the linear regression and the decision trees, the trees are much easier to interpret. And the linear model is considered as, in terms of the comprehensible, linear models are considered as between medium to high. We can interpret the weight as the importance of the feature, and the choice often depends on who your stakeholders is. So what if, because in a linear model we consider that the relationship between the variables is linear, and what we mean by linear is it should be a straight line. But what if a straight line is not enough? So we can always add the complex feature, like we can take the square of the x, or we can add in the interaction terms, like for example x1 multiply with x2, and here from these interaction terms we get what we call as the synergy effects, and this will allow the linear model to represent a curved boundary, for example like parabola, which is not a straight line but instead more like a curve. Now let's briefly talk about neural network. Neural network, you can think of this as a stack model where you have like several layers. So the first layer may learn simple model, or it can become an expert in different facets of the data, and then we have the next layer, which is layer 2, which learn how to weight those experts' opinion. And imagine something like this, where let's say in the layer 1 you have model 1, model 2, model 3, and this model is considered as the expert who know how to build a predictive model based on the data that we have. But expert number 1 may say a little bit different thing than expert number 2. So what you do in the second layer is that you take the weighted opinions of the experts in the first layer. So a neural network is extremely flexible, and it would require a careful tuning because it may cause what we call as the overfitting. So what exactly is overfitting? So let me talk about this major warning, the danger of overfitting. So overfitting is when you try to fit the model as perfect as you can. So imagine like when you go for a tailor to make your dress, and imagine if the tailor is making a dress and is measuring your body, and then they sew a cloth that is perfectly fit to your body. So what happens is that this clothes is perfectly fit to your body, but when you try to generalize, or when you try to use this clothes to any other people, they might not be feeling comfortable, because the measure is done accurately according to the curve of your body. Okay, so that's also the same as in the model. So basically, the flexibility might, in this case, might become like a double-edged sword. So the more parameters we have, the better we are at training the data where we get a perfect fit, but we may cause the model to be overfit, and the model captures some random noise rather than just general truth. So we must always balance the goodness of fit with model simplicity. So the important part here is that we do not want the model to be a perfect fit to the training data, because we want to use the model to predict a new data, and we want the model to contain only the essential parts where it can be generalized when the new data comes in. Now let's wrap up. Our key takeaways is that model, we have to remember that model is not supposed to be something that can be accurately predict every data points in the training data. We want the model to become a simplified representations to only contains the essentials of the main patterns that can be used for to generalize it using a new data. And the parametric modeling is a model that fits weight to fixed equation, and linear discriminants create global boundaries, and objective functions define what best would mean. And remember, logistic regression is for probabilities, and the support vector machine is for fat margin classification. So think about the data analytic thinking in practice. Don't just pick an algorithm. You should ask yourself, do I need a category or a probability? Do I need to explain the why to a manager? So is the boundary a simple split or a complex trend? So I'll leave you with this discussion question. So let's say if you're a bank manager, would you prefer a decision tree or a logistic regression to decide on the loans application, whether or not you want to accept or you want to reject certain loan application? And how would that change if the law required you to explain every rejection to a customer? Think about that for next time.